Okay, now we're going to cover reflection. So before we can get into how reflection works, we need to know what a light ray is. So if we have some water waves that are crashing upon a beach, the water waves look sort of like this. And the tops of the waves right here, these are going to be our wave crests. So if these are the wave crests, then the distance from crest to crest, that distance right there, that's going to be our wavelength. So the wavelength is the distance from here to here, or it could be from here to here. The bottom of each wave, these sections right here, these would be our troughs. Now, this is a difficult diagram to draw for physicists. We don't want to always be drawing water waves in a beach. So if you can picture looking at this top down, we would only see, like from a helicopter, we would only see lines of these crests. So a top-down view would just look like this. Now, we know that the waves are moving towards the beach like this. So instead of drawing the waves always as crests and troughs like this, we can draw a light ray, which is just a straight line that represents the direction of the wave motion. Now, for circular waves, we can also draw light rays. And again, light rays, or it could be sound waves, it could be any wave, travel in straight lines. But in this case, we have concentric circles. So this is like a rock that's dropped in a pond, like we've seen before in the other parts. And the way that the wave fronts are moving, we can think of each of these as being parallel to one another. So our light ray is propagating out like this. So if we want to draw these light rays coming in all together, like this, here's our wave fronts, and our wave fronts collide with the surface. And what happens when waves collide with the surface? Well, they bounce off. And the way that they're going to bounce off is they're going to hit this, and they're going to bounce off like this. Now, this ends up becoming a very confusing diagram because we have light rays coming in like this and then light rays going out like that.
So here come the waves, and they bounce off the boundary just like that. But now let's look at this a little more carefully. And the way we're going to do this is so we can make some measurements. We're going to draw a reference line, which is called a normal. And we're going to put the reference line right here. The reason we call it a normal is this line is perpendicular to the barrier. So that's going to be our line that we use to represent the waves, represent the reflection, and to make measurements. So let's let the waves advance here a little more. And we want to represent these waves. So here's the waves all coming in with one line. We're going to use one arrow, and we're going to draw it like this, and this arrow is going to represent the waves coming in, which are called the incident waves. And we're going to let them reflect. Now you can see them reflect off the barrier, and notice here's the waves that have reflected. And what we want to do is compare the direction of the waves that have come in, which are the incident waves, and with the direction of the waves that have reflected. So let's get another arrow, and this arrow is going to represent the direction that the waves have bounced off of the barrier.
So rather than draw all these wave fronts, what we do is we draw our surface, and we draw what's called the normal line. The normal line is just like the normal in the forces unit. It's a line that's perpendicular to the surface. Then we draw our light ray, which comes in like that. And then we draw the outgoing light ray like this. Now, this incoming light ray is called the incident ray. And the outgoing ray is called the reflected ray. So I'll add the word ray here, like that. And there's a relationship between the angles that are in here, and we'll see that in just a second. Okay, so we just discussed this as the incident ray. So angles are always measured, and this is important. They're always measured from the normal. So when we look at this, we have to be very careful not to use this angle in here. This is the angle between the ray and the surface, and we want the angle between the normal and the ray. So our angle of incidence, theta I, is right here. Now, if we have our angle of incidence coming in like that, we can measure it. So we're measuring from the normal. So we go 10, 20, 30, 40. So our angle of incidence is 40 degrees. So our angle of reflection is going to be the same on the other side. So we can say 10, 20, 30, 40. And we can make our reflected ray. So here is our reflected ray. And that's going to be measured from the normal to the ray, theta r, and that is also 40 degrees. So what's our definition here? Our definition is that theta I is equal to the angle of incidence. And just remember that the in helps you to remember that it's into the surface. Theta r then is equal to the angle of reflection. And that's the outgoing ray, the one that is bounced off the surface. So there's a law here, and the law is called the law of reflection. And this is probably the easiest formula on the reference table. The law of reflection simply says that the angle of incidence is equal to the angle of reflection. So if you know theta I, and that theta I is 40 degrees, theta r has to be equal to that. It's 40 degrees. So whatever angle it comes in at, that's equal to the angle that it goes out at. So how can they make these questions more difficult? Well, they could give you a diagram like this and not give you the angle of incidence, instead give you some other angle. Well, we know that the angle of incidence is here. And we know that the normal is at 90 degrees. So if this is 60 minus, or 90 minus 60, that means this angle has to be 30 degrees. What's another way that they can make this question tricky? They could give you the two rays, the incident and reflected ray, and give you the angle between the rays. So if the angle between the rays is 70, we know that the angle of incidence is 35 degrees and the angle of reflection is 35 degrees. Now, not all surfaces are perfectly smooth. If the surface is smooth, then all of the rays would come in parallel to each other and they would reflect out parallel to each other. This has a name. It's called regular reflection. There's another name for this, which is called specular reflection. And this isn't as common. Usually it's called regular, but you should know specular reflection as well. And examples of this would be mirrors, because mirrors are very flat, and also anything that's shiny. A shiny object is going to be reflecting the light as regular reflection. This here, when we have a rough surface, this is called diffuse reflection. And diffuse reflection occurs when the surface is rough. So an example of that would be a rough surface. Now, it may not seem that paper is rough, but at the microscopic level, it is. So in this case, the law of reflection still holds true. You can see it's kind of a difficult diagram to look at, but we have our incident rays are all coming in nice and parallel to each other, but they're reflecting off at all different angles. But it's still holding true that each little surface has its own normal. So the normals are jumbled up, which gives us this jumbled up reflection pattern. And you can see your reflection in a regular reflector, but you would not be able to see your reflection here. You can see your reflection in a mirror, but you can't see your reflection in a piece of paper. Now, if this was a car that hasn't been washed in a while, the car isn't going to be shiny. But imagine you put some wax onto the surface. So here's your surface, and you put some wax over the top of it. Then you polish that wax away. The wax fills in all of the little crinkles and crunkles, all these little areas in here, and makes a flat surface, which is why your car becomes shiny after you wax and polish it. Refraction is a phenomenon where light bends, or any wave for that matter, so it could be sound, as the wave travels into a new medium of different index of refraction. Okay, this also has to happen obliquely. So let's break this down more specifically. Refraction is bending of waves. Now, there are other phenomena that can make waves bend, so you have to be very, very careful, because refraction is bending when these other conditions are met. So the first condition is that the wave has to be oblique. So what does oblique mean? Oblique means any angle other than 90 degrees to the surface. So if a light ray comes in on the normal, it is not oblique. So if there's an angle of incidence, some angle other than 90 degrees in here, then it's considered oblique. Between different mediums of different index of refraction, this means there has to be a speed change. So if there's a change in speed and it's oblique, this wave will end up refracting. Now, before we talk about the actual bending, let's first look at an example where the light changes medium but does not bend. So this is not refraction. If we have a wave, and here's our wave fronts, we know that they're traveling down like this. So they move into the new medium. The new medium has a higher index of refraction, so it will slow down. So here the wave fronts are spread apart, so the speed is high. It's traveling at a high velocity. And the frequency is some frequency f, and the waves are spread out, so the wavelength is large. And we know this from the last unit, that when we go into a new medium, the frequency does not change. So what has to change? The speed gets slower, the frequency remains the same, and the wavelength is the only other thing that can change, so the wavelength gets shorter. But what type of question might they ask you? They might give you something like this. They show you a light ray coming into a new medium, and they'll ask you, what will it do? And the answer is, it's just going to go straight through. Why? Even though it slows down, even though it changed mediums, it did not come in obliquely, so in this case, it does not refract. So let's look at a situation where refraction actually occurs. So we have a medium, let's say 1.00, and another medium, endpoint 2.00, and what happens is these light rays come in and they hit the new medium and they bend. So this is refraction. Now, why does refraction occur? Well, it happens because the light waves are changing speed. In this case, they're slowing down. Now, refraction will also occur if we went from a higher index of refraction to a lower index of refraction. We can see that they're oblique, and basically what happens is you can picture a light wave coming in like this. It's moving fast, and as soon as the bottom of the wave gets into the new medium, this goes more slowly. So as this starts to go slowly, it has to bend. So the light wave does something like this as it moves into the new medium. So rather than draw it like this, we draw our light rays. And the diagram looks like this. So we have our index of refraction of 1.00, our index of refraction of 2.00, and here is our incident ray. Where's it measured from? It's measured from the normal. Now, this ray is going to move into the new medium, and it is going to slow down. that slowing down is going to make it bend towards the normal. Now that's very important. I'm going to label this theta r. Theta r is our angle of refraction. Now I use an uppercase r because, and most textbooks use this as well, because we don't want to confuse it with little r, the reflection. Every time we have light traveling into a new medium, there is going to be refraction if it's oblique, and there's also going to be reflection. So we're always going to get both of these. We're going to get theta I and we're going to get theta r in addition to refraction. Now we can say, sort of as a rule here, as long as it's oblique, slowing down, when it slows, it's going to bend towards the normal. And we'll do this next with the opposite case, where it speeds up, and as you could guess, it would bend away from the normal. So theta r is the angle of refraction, and it's very important, just like we did for these. The angle of incidence is measured from the normal to the ray. The angle of reflection is from the normal to the ray, and also the angle of refraction is measured from the normal to the ray. If you make a mistake on these, the formula that I'm going to show you will come out wrong. So make sure you always measure from the normal to the ray.
So next we're going to take a look at refraction. So what we've got is a plastic block in here that's going to change the depth of the water. So let's send that through. Okay, so you can see the wavefront being bent as they travel over the shallower section. Okay, so as the wavefront travels along, the wavefront doesn't change until it encounters the boundary. So you can see the wavefronts which have to travel further stay the same for longer, whereas the wavefronts where it hits the boundary first of all change direction earlier.
Here's how we define it in simple words. It's simply bending of light when it travels from one medium to another. Yes, if it is incident at this angle, then it goes through at another angle. Now this is not the exact definition, as there are a few technicalities involved. Let me explain it to you. Consider a transparent object kept here, say a glass slab. Suppose light traveling through air is incident obliquely on the surface of the glass. What do I mean when I say obliquely? It means slant. It implies that the incident ray is neither parallel nor at a right angle to a specified line. Now this light will bend at the boundary of the two media. Here the two media are air and glass. This bending of light at the boundary of the two media is what we call refraction of light.
So here's the other example of refraction. Again, our angle is oblique. It's not coming in on the normal. And we're changing mediums, so therefore we're going to get refraction. And if we're going from 2.0 to 1.2 or 1.0, we're going to speed up. So here's our ray that's incident, and here is our refracted ray going out like that. So what does that look like on our diagram? Remember that we also get reflection, so we're going to have an equal angle over here, theta little r, and then it's speeding up. Now speeding up means it's going to bend away from the normal. So in this case, our theta r is larger than our theta I. So when it speeds up, it's going to bend away from the normal. So how can we actually calculate these values? How can we actually figure this out? Well, we need a formula, and that formula is called Snell's law. So here is Snell's law. Snell's law says n1 sine theta 1 equals n2 sine theta 2. n1 sine theta 1, that's our medium 1. So that's what the incident ray is in. So that's medium 1. n2 sine theta 2, that's our medium 2. That's where our refracted ray is. So really it's 1s and 2s, but we can say n1 is medium 1, Theta 1 is theta I, that's our incident angle. N2 is the second medium, what it's traveling into. And theta 2, that's going to be our angle of refraction. Now, this is on the reference table right here, so we don't need to memorize it. It's in the waves section. So let's actually solve a problem. Let's say we have an incident ray, and that incident ray is in water, and it's hitting a new material called zircon. Now, I looked up these numbers in advance, but they are on the reference table. We have water is 1.33 and zircon is 1.92. So, what's happening? Well, it's going to a higher index of refraction, so it's slowing down. So this is our N1 and this is our N2. Well, if it's slowing down, we already said that it must bend towards the normal. So this theta r is smaller. But the question is, what is this theta r? What's the value? Now don't forget, we also have our angle of reflection occurring too, and they may ask you to include that in your diagram in a question. So let's go ahead and solve it. We have N1 sine theta 1 equals N2 sine theta 2. And what's our N1? Well, that's our medium 1 of water. So that's 1.33. No units on the index of refraction. Sine theta 1, that's our incident angle. That was 60 degrees. And our N2, that's our new material, zircon, 1.92. And sine theta 2, what is that? That's what we're looking for. That's our angle of refraction. Now, to do this, we are going to do, make sure your calculator is in degrees. We're going to do 1.33 times the sine of 60. And that gives us a number, and then we're going to divide by 1.92. Now, here's where people make mistakes. We get an answer of 0.599, but that's not the answer to the question, because that's the answer to what sine theta r is. So we haven't solved for theta r, we've solved for the sine of theta r. Well, how do we get the opposite of a sine? Well, we have to do the inverse of sine. So we're going to put in our second sine. So that's going to be second sine, which is sine to the negative 1. Then we're going to put in our 0.5999, and we get a value of 36.9. So our theta r is 36.9. So when we go back to our diagram here, we had our incident angle of 60, our theta r over here is 36.9. That makes sense because it refracted, it bent towards the normal, so this number should be smaller than this number. Let's do another problem, this time where we go from our N1 to our N2 and the numbers decrease. So we're going to a lower index of refraction. What does that mean when we're going to a lower index of refraction? That means the wave is going to speed up. And we know that when the wave speeds up, it's going to bend away from the normal. So this new theta r is going to be larger than our theta I. Remember, we always get reflection, so we can throw that in, and that's the easy one. They are equal. So let's go ahead and solve for our theta r, our angle of refraction, and that's going to be N1 sine theta 1 equals N2 sine theta 2. Our N1 is our initial material. This time it's zircon. And our angle of incidence, our incoming angle, is 30 degrees. Our N2, this time it's passing into water, so that's 1.33. And our sine is our sine of our angle of refraction. That's our theta r. So what do? The same thing that we did before, which is we put in our 1.92 times our sine of 30, and then we're going to divide that number by our 1.33. Now, here comes the part you have to be careful not to make a mistake. We get a 0.7218 is equal to the sine of the angle of refraction. How do we do that? Well, we hit our second sign, and then we put in our 0.7218, and our second sign, remember, is the inverse sign, and we get an angle of 46.2. Now, take a look. This angle is larger than the angle of incidence, which tells us it bends away from the normal, and that's what we would expect. This is a more advanced question where we have the light going into a new medium and then exiting out on the other side. So, for example, we start out with air, and then we have our ray enter flint glass, which has an index of refraction of 1.66, and then it leaves the other side going back into air. And what's this ray diagram going to look like? Well, we have our incident angle, and I did n1 sine theta 1 equals n2 sine theta 2, but we've already done 2 examples of this, so you should know how to do it at this point. And that theta r that comes out on the other side is 31.4 degrees. So I measured this with my protractor and came up with 31.4, and it meets the other side right there. So I'll draw that ray in, and that is our refracted ray. So that refracted ray is 31.4 degrees. But what's going to happen when it enters air? Well, we have a new medium that it's hitting, so we need a new normal. So that new normal is going to be this line right here. So we have our 31.4 as our refracted ray, but these two lines are parallel to each other. So this angle right here has to be equal to this angle right in here. So that angle is also 31.4 degrees. And if you think about it, this becomes our theta I. So our theta R for problem 1 becomes our theta I for the second half of this problem. Well, if it's 31.4 coming in, we can do n1 sine theta 1 formula, Snell's law again, and what you'll end up getting is the same exact number in reverse. 10, 20, 30, 40, 50, 60. You'll get 60 degrees coming back out. So if the first material that it enters in is the same material that it exits, that angle of incidence originally will be our final angle of refraction at the end of the problem. There's one more thing that you should know about these problems, and that is that the problems are reversible. So if we start out with n equals 1.00, entering into n equals 1.66, our flint glass, we get an angle of refraction of 31.4. But what if the light rays were going in the opposite direction? Well, all you're doing is flipping around n1 sine theta 1 equals n2 sine theta 2. You're just putting 1 on the other side. So what is the angle of refraction from the problem before becomes our angle of incidence in this problem. So this light ray will go out at exactly 60 degrees. So if it comes in at 60 and refracts at 31.4, then the same thing is true in reverse. The incident angle of 31.4 will produce an angle of 60 degrees. That's its angle of refraction. So there's an interesting phenomenon that will happen when you have light traveling from a higher index of refraction to a lower index of refraction. And that is that there's something called a critical angle. And the definition for a critical angle is the angle of incidence. So this is key. The critical angle is an actual angle of incidence. It's a very specific angle of incidence. It's the angle of incidence that makes light refract 90 degrees. So if we come back to our diagram here, we're saying that the angle of incidence is going to make the light refract, and it's going to make it bend away from the normal. But there's a certain specific angle that will make light refract so much that the angle of refraction, this angle right here, theta r, becomes 90 degrees. Now, if we exceeded that angle, it can't refract more than 90 degrees because there's nothing for it to bend into, so therefore it reflects back into the diamond, and that's called total internal reflection. So let's go ahead and solve a problem. Let's solve for the critical angle of diamond. So we're starting in diamond, and we're going to use Snell's law. N1 sine theta 1 equals N2 sine theta 2. And we start in diamond. So our initial N is our 2.42. And our sine theta 1, that's going to be the critical angle. That's what we're searching for. And that's equal to N2, which was air in this case, 1.00. And that's equal to sine theta 2. And here's the crucial part. Remember, this is only going to occur when you go from high index of refraction to low. It never happens the other way around. So the angle of incidence is our critical angle in this case. And what's it doing? It's making light refract at 90 degrees. So we know theta r. What is our theta r? Well, that's sine of 90. Sine of 90 is 1. 1 times 1 is 1. So we have 2.42 times sine theta critical equals 1. And we go ahead and put our numbers into our calculator. And I've shown you how to do that, so I'm not going to do that again. And our critical angle comes out to 24.4 degrees. Now let's go back and look more specifically at what's happening. This angle now, our critical angle, is 24.4 degrees. So let's get rid of this for a minute and just look at what happens. If we have an angle that's greater than 24.4, something that's out here, then what that's going to do is make the light refract into the medium at some value that is going to make it bend towards normal, or away from the normal. But as this angle starts to get smaller, eventually we reach a point where the refracted angle is so large it becomes 90 degrees. But if our angle of incidence is less than the critical angle, then there won't be refraction at all. All we'll get is reflection, and that reflected angle is equal to that angle of incidence. So the definition down here, and listen to this carefully, if the angle of incidence is less than the critical angle, all of the light will reflect back into the original medium. And what's the name of that? That's basically the definition for total internal reflection. So we've talked about reflection and refraction, but there's one last piece that we have to talk about with reflection, and that deals with ray diagrams. So let's say this is a surface of a mirror, and we have an object, this could be a matchstick, that's at an angle set in front of this mirror. Well, what's the image going to look like of that object? Well, we can do this with ray diagrams. So let's say we have a ray of light that travels in like that, and that's our incident ray. So our incident ray travels to the mirror, and it comes in on the normal. So what's it going to do? It's going to bounce out on the normal. Now, I didn't mention that before, but it's almost completely intuitive that what's the angle of incidence for a light ray that's coming straight in? Well, its angle of incidence is 0 degrees. So the angle of incidence has to equal the angle of reflection. So theta r, the angle of reflection, also has to be 0 degrees. So the light ray just comes straight out. Now, if we have a second light ray that comes off of the tip of the matchstick, it's going to hit, we're going to have our normal here, and it's going to bounce out at the same angle. Now, if we trace these rays back, this can help us to find the position of the object. So if we do this like this, we get this going back here, and where they cross, that point should be equal to this distance of this point right here. So this is our object distance and this is our image distance. And this distance and this distance are the same. So it travels through like that. And we can do the same thing for the bottom. Let's say we have a light ray that comes in like this. It comes in on the normal, so it bounces back out at the normal. And let's say we have a second light ray that comes down like this, hits, and I'm not doing this with, fully with the protractor. I'm just eyeballing it, so it's not perfect. But if this angle comes out like that, then we can trace this ray back, and we can trace this ray back, so that this distance right here has to be equal to this distance right here. So this is called the object distance, and this is the image distance. And now we can see that what we have is a reflected image of the object. So this is called a virtual image because it's not real. And it is only the result of the reflection of the light rays, and this whole diagram is called a ray diagram. So the object like this is reflected in reverse on the other side. So you might be asked a question like this: if we have the word red, then what's that going to look like in the mirror? Well, it's going to be reversed. And if you've ever worn a t-shirt or a hoodie that says some words on it, when you look in the mirror, it is reversed. And that's because the distance, think about the distance from that point to here, that has to be equal. My diagram's off a little bit. And this distance is further, so this part is further. So the word ends up reversing. The last thing that you need to know about reflection is that when we have an object, so it's, in this case we have a candle, and it's set some different distance away from the mirror, that distance has a name, and it's called the object distance. Well, the reflected distance has to be exactly the same, and we just said that before. So there's kind of a silly formula for this, but this is called the image distance, and we know that they have to be equal. So what's the formula for that? DO, the object distance, has to be equal to the image distance. So let's say that this is 5 centimeters away. Well, then the image distance also has to be 5 centimeters. But the question might say, how far is the image behind the mirror? The answer would be 5. But the question could also be tricky and say, how far is the object from the image? And that answer would be 10 centimeters. There's a way to make this question even trickier. Here's our mirror. Let's say that a person is located 5 meters from a mirror, and there's a chair in front of them, and that chair is located 2 meters from the mirror surface. But the question actually asks, how far is the person from the image of the chair? Well, where's the image of the chair? The image of the chair is going to be 2 meters behind the mirror. So how far is the chair from the person? That's going to be 5 meters plus the reflected distance, the image distance of 2. So the answer would be 7 meters. Lastly, this course doesn't go into the details of this, but we have things that are called concave mirrors, in which light comes in and reflects off like that. We also have diverging mirrors, where light would hit the back of this and bounce off like that. And there are also different types of lenses, diverging lenses and converging lenses. But this course doesn't go into it, but what you should know is that this will change the size of the image, and it will also change the distance of the image, DI.